Hi there. I'm Tom Quilter. I have a PhD in evolutionary game theory from a fair few years ago. After that, I worked as an investment banker, and then I quit to become an inner city school maths teacher in London for a while. During my time as a teacher, I programmed a personalized education website called Pinpoint Learning. The last 5 years, I've been fascinated by machine learning and have been studying a lot of my spare time. And I actually would like to go into academia in machine learning. As such, for the last year, I've been working with Professor Richard Turner at Cambridge and two of his grad students, Anastasija and Karen, in a purely academic collaboration on finding a prediction model for the education data from my website. So the main aim of the paper is to be able to predict whether a student will get a question right or wrong, where we have a lot of data on students answering maths questions. So given their previous data and all of our data, how well can we predict whether they'll get an unseen question right or wrong? Why do we care? We're just really interested to see how well we can predict it. We're also, if we can come up with a good prediction model, we can create a very personalized revision platform where we can serve up questions of exactly the right difficulty for different students, highly personalized to them. We're fascinated to see if we can find some underlying features of the student's mathematical ability. If we're able to break down a student's ability into hidden elements that that the teacher doesn't know, the pupil doesn't know, maybe the teaching education community doesn't know. This would be really fascinating. It's still quite unknown what makes a student good at maths compared to a student who's weaker at maths. It's something the machine learning community is excited about. In 2020, NeurIPS issued an educational challenge which had over 400 submissions throughout the world. The data comes from my website, Pinpoint Learning. The data itself is from GCSE mock exams. Some of you may have sat these. They are 16-year-old exams. And during the ages of 14 and 15, teachers prepare their students for these exams by giving them mock exams in class. They are exams of about 25 questions. They're not multiple choice, they're written exams. They're out of 2 or 3 or 4 or 5 marks. You can see a couple of them here. We think the data is of high quality because they are questions that are done in exam conditions. They're marked by a teacher, and then those marks are individually uploaded to the website, the individual questions. The website takes that data and makes personalized resources for them. And we think this is high quality data in that it's not just a student on a computer answering multiple choice questions quickly. Results so far are from 50,000 students and 70 questions. We're working on larger data sets currently, and we've got more data to work with. The data looks like this. So we have in our first set of results, we are looking at 70 questions and 50,000 students. Here's an example of the questions. Question 1 is an algebra question out of 5 marks, where questions can get between 0 and 5. Most of our results are from binarized data, where we assume that if a student gets half the marks or more, then we'll call that correct. The model we're using is fairly standard machine learning, just to get a baseline result. This is from item response theory. We have 2 parameters, one for the student ability and one for how hard the question is, such that if we have a clever student and an easy question, there's a high probability of the student getting it right, and vice versa. A low performing student and a difficult question, there would be a low chance of getting it right, and then the whole continuum of probabilities between those. Some of you might notice that question is quite difficult. The set of parameters is estimated using the maximum likelihood estimator. This does not have an analytical solution. We use gradient descent, and this has been proved to converge to a global optimum. The results from our ability difficulty model are as such. There's a smooth convergence. We split the data as so into the training test and validation set. We get an accuracy from this of 80.5%, which we think is quite a good initial result for a non-complex model, indicating the quality of the data that we've got. We've done a couple of other baselines. We ran a model just using the student ability where we don't look at how hard the question is at all. That gives us 61%. If we look at the question difficulty without looking at the student, we get 64%, gives us a little bit more. This is the model we've already spoken about. And we are currently and have been researching an interaction model where we look to break up the student ability into set number of sub features and the question ability into corresponding sub features. And here we're looking to take advantage of the similarities amongst the students and amongst the questions and any underlying latent features in order to improve our model and to discover what's going on behind the scenes with the students. So far, this has led to a small improvement, but statistically significant. We're investigating now using a larger data set, using optimizers, and possibly more compute, because the log likelihood is no longer convex, and we might be stuck in a local minima. So we're having a look at that too. We've also looked at active learning, where we're given a set number of questions. How accurately can we predict the student's ability there? This could be very interesting for a new student who comes onto the platform. We're trying to work out how quickly we can assess how good they are and how well we can predict their mathematical ability. We've used pool-based active learning and found some interesting results by selecting the most uncertain questions available. We have also looked at an ordinal model where we are trying to predict the exact mark. So if it's a 5-mark question, how accurately can we predict that that student will get 3 out of 5 or 1 out of 5 or 2 out of 5, not the binary model. And this is currently at 66%, which is quite high, and also allows us to do some good predictions on a student's overall exam results, which could be very powerful. The next steps are we're looking at much larger data set in order to see how the results adapt from there, introducing more complex models, using optimizers for the interaction model, and investigating the impact on metadata. But this is a brand new data set that we've got here, and so there's a lot of interesting work to be done. Thank you.